some idea about the work and energy, which is another way that we can solve an object in motion. This method actually has some benefit. One of the biggest benefit is that you don't need to worry about the direction. There's no vector at all in this case. So all you need to do is to find those quantities, and you have to know how do we define those quantities. Equation itself is very simple. We will write down the equation. And we also need to tell you the property of all these quantities, and we're going to show you some example to that you understand why that we define in that way. So chapter 6 talk about work and energy. We have many kind of energy, but we're going to start with one a very specific energy, which is called the kinetic energy. The other thing that we're going to define is the work. So we're going to define the work. We're going to define the kinetic energy. And the last thing we're going to do is we're going to combine these two. And when you combine these two is what we call work and kinetic energy theory. So we're going to show you that energy equation as well. Over here, you can see that we define the work already. So the work is a quantity of the energy required to move an object over a distance by a force. Now, it's probably the simple way to see this is just make a drawing. So I'm going to show you an example. What do we mean by work? The simplest case is that this is a flat ground, and we put a box over here. This box has a mass, and if it just sit there, there's nothing going to happen. But if you apply a force, which means that you push it, then this box will start to move. And when it's going to start to move, then in the previous chapter, we know how we can write the equation. This equation is the Newton's second law, which is the F equal to ma. Then you can find the acceleration. So this equation helps you to relate the force and also the acceleration. This is a Newton's second law. And if you know the acceleration, you can also find the velocity, right? How do you find a velocity? Well, if you have acceleration, this is the constant acceleration motion, and we have three equations to help you to find different things. One is to find the displacement, and there's two equations to help you to find the velocity. So one of the velocity you can find is using this equation. But you need to know the time. What if I didn't give you the time? What if I told you, when I apply a force and this object will move, and it's going to move with certain distance, and this is a distance. After I move this box with a force over a certain period of time, I'm going to see the box move with certain distance. Then how do we solve this? Well, certainly you have another equation you can use. That equation is this equation. And that equation helps you to relate the displacement and also acceleration and also the velocity. So these are very useful. We can solve in this way, but we're going to tell you another way to solve this problem, which is the work and energy. So let me define the work first. just by looking at the definition that we give you, the work is a quantity of energy. So this work is actually an energy. Kinetic energy is also an energy, but the work is done by a force. Kinetic energy is an energy if things is in motion. When we say things is in motion, meaning it has a velocity. So this is the energy related to the motion, and this is the energy related to a force. If you watch the pre-lecture, and this is how we define the work. A simple way to define that is just simply a force times the displacement or the distance. But it's not like all distance counts. It's the distance along the direction of the motion. Only the distance that is go along with the direction counts as the work. So for example, if you use the same idea that we have at here, let's say this is f of 1. If I at the same time apply another force, and this object will move to the right. If you at the same time give a force f of 2, which is perpendicular to the motion, then the f of 2 is not going to do work. So if you are not parallel to the motion, you do zero work. Well, it's only when you are perpendicular. When you are perpendicular, when the force is perpendicular to the motion, it's going to do zero work. If the force has a certain angle, then you might do some of the work, but some of the force is not going to give you any of the work. Because in the previous chapter, we know this force with an angle, you can decompose that into two, and one is going to be perpendicular or one is going to be parallel. This one F3 of X, this one F3 of Y, which one perpendicular to the motion? The F3 of Y, because it's going downwards, but motion is going to the right, so they are perpendicular. If they are perpendicular, they are not going to do any of the work. It's a waste of the force. Only the force that is parallel to the direction of the motion is going to give you the work. So that's very important that you have to know this. The second thing about the work is this. The work can be positive, it also can be negative. You can have a positive work, negative work. Work doesn't have a direction, is not a vector, is a scalar, but it have the sign, it could be a positive or it could be a negative. And what does it mean, the positive? What does it mean, negative? When you have a positive, meaning the force and the motion in same direction. If you put to the right, an object move to the right, that means you're doing a positive work. But you can also have the force go to the opposite direction with the motion. What is the case that you will have a force and motion in the opposite direction?
Friction.
Yes, great. Friction. Friction is the best example that you can think of. When you have things move to the right, friction is going to be on the opposite direction of the motion. So friction is one of the example that will give you a negative work. Okay, if you think about the motion, the result of doing a positive work is you're going to accelerate the object. Meaning you're going to have a positive acceleration. And this one here, if you do a negative direction, it's going to slow down the motion. Just like the friction tries to slow down the motion. So that's something to do with the work. Okay, one of the forces that we see a lot is the gravity. Do you think gravity will do work? Well, if the gravity is a force, and if the gravity can make something move, then certainly gravity can do work. An example is going to be like a free fall. If I have an object over here, it has a mass, I know it's going to have a gravity force, which is m times g. That's the weight. One of the exam problem asking you the difference between the weight and the mass. A lot of people still make mistake by writing the mass as the weight. So I just wanted to emphasize that. Mass is in kilogram, force or the weight is in Newton. So mg is the weight. If you drop an object and this object will drop for certain height, let's say it dropped 2 meters, then are there any work done by the gravity? Yes, because it moving downwards and the force is going downwards. They are parallel. Okay, and let's say if this is 1 kilogram, then the weight is going to be 1 multiplied with 9.81, and that will give you 9.81 Newton. Then you can calculate the work. So the work is equal to this. It's the force, where the force is the weight, is 9.81 Newton, and multiply with the distance along the direction of the motion. And how much distance is that? Well, along the direction is 2 meters, so you multiply with 2 meters. And that will give you the work. Wow. And keep the 366, that will be my work. So that's how you calculate work. So the unit for the work is Newton times meter. But we also kind of lazy, we wanted to use a simple symbol to represent it. Newton times meter is also called the joule. Or simply just write a J to represent that. Okay, so this joule is the SI unit for work or for energy. You probably heard about different kinds of a unit for the energy. What is the energy unit that you heard before or we use the most? What about this? Calorie. We use calorie to represent energy as well. And that's another way you can quantify the energy as well. They define in the different way, but they represent the same thing. It's the same, just like our meter as opposed to the feet. And very interesting about these two is if your work is done, if the energy is generated mechanically, then we use joule. Mechanically meaning the energy is generated by force. Calorie is energy generated by heat, by like something changing in temperature. When you have the energy generated by that way, then we will use the calorie to represent the energy. But we can also do a conversion. We can convert these two, and you are going to learn this in the later part of this course. When we toward to the end, we will look at the energy by looking at the temperature change. But you have to remember these two are all the energy unit. We're going to use the joule for the most of the time in this part. So remember the Newton times meter represent the energy, which you represent as the joule. Okay, so that is what the work is. The second thing we're going to define is the energy. In this chapter, we're going to talk about several different kinds of energy. But at this moment, we just wanted to focus on an energy is related to the motion. And we will focus on the mechanical energy. There are two types of mechanical energy. One is kinetic energy, which we use Ke to represent it. Another one is the potential energy. And we use Pe to represent it. So mechanically, you can generate energy by given kinetic energy or potential energy. These energy are due to different factors. The kinetic energy is due to the motion. The potential energy is due to the position. We're going to focus on the potential energy next time, but let me just look at the kinetic energy first. The equation for the kinetic energy is this. If you have an object with a mass, which is m, and it's going to move with certain kind of speed, then the speed squared times n divided by 2 is how we define as the kinetic energy. If you use the unit and you multiply, then you're going to find out this is actually the result of that is going to be Newton times meter, and which is the joule. The potential energy is the energy due to a force at a different height. And one of the important potential energy is actually the gravity. That we will talk about this later, but at this moment, we're not going to use the potential energy, so we're going to just focus on the kinetic energy. So how do we find the kinetic energy? Just give you some simple example over here. Again, we're going to move, let's just say I have a block here again, and it's moving at this direction. And let's say this one is 10 meters per second. And we give you this one, which is this object is 9.8 Newton. As moving to the right was 10 meters per second. After it moved to the right, at certain position over here, we're going to say this one has the speed, which is 5 meters per second. Then I want to ask you, what is the kinetic energy of this object? And you look at this problem, the velocity of this object has two different values. And because they have two different values and their mass is not going to change, that means the kinetic energy is going to be different. Kinetic energy depends on the state at that moment. So if you look at what position that is and what velocity that is the kinetic energy at that moment. So if we wanted to look at the kinetic energy, if we look at this one, let's say this one is the initial position. This is the final. What is my initial kinetic energy? Equation is very simple. 1/2 mv squared. This is your initial velocity, which is this one here. This is my final velocity. And it's the same equation that you use, you can find out what is the final kinetic energy. So if you put the value into this equation, what will be the value that we put in here? What is my mass? Well, this is one of the mistakes people will make. You're given with 9.8 Newton. 9.8 Newton is not mass, it's a weight. So if you want to find a mass, you have to put the 9.8 divided by the g, because this one is equal to m times g. So your mass is actually 9.8 divided by 9.8, which is 1 kilogram. Okay. And what is my initial velocity? It's 10 meters per second square. And that will give you the kinetic energy at the beginning. So that's 1/2 times 1 times 10 squared, which is 100. That's 50. And the result is going to be Newton times meter. And this is also what we call the joule. So this is a 50 joule. Let's look at the final state. Final state, you have the same thing, same equation, 9.8 divided by 9.8, which give you 1 kilogram. And you multiply it with the 5 meters per second squared. Yeah. And that will give you what? That will give you 1/2 times 1 times 25. That will be 12.5 Newton meter, which is 12.5 joule. So that's how you find the kinetic energy. And when you look at this one here, if things start to move to the right and it slow down, what happened? If it slow down, it must has a reason. And the reason is that you actually apply a force. And when you apply a force, do you apply force to the right or you apply a force to the left? In this case, your force is going to go to the left. Otherwise, your force is going to make it moving faster. And it moves slower simply means there is a force that moving to the left. And what does this force usually be? This is your friction force, right? That means you have a friction force. And if I told you, well, this one moved from here to here, and the distance of this is simply equal to 1 meter, then can you find a friction force? In order to find that, then we have to understand if you change the energy, the reason that you can change the energy is because of the work. If you didn't do any of the work, then we have a so-called conservation law. The conservation law says the energy is always going to be conserved. Energy can change different form. You can change from kinetic energy to other kind of energy, but it cannot be destroyed. It cannot be created. The only thing that you can change the energy is to give work. So the work is the reason that you have a change. So I'm going to write this one here. The work and the energy, kinetic energy theory is work is equal to the change of kinetic energy. You can also say, use the symbol, the triangle represent the change, the delta kinetic energy. When we look at the change, it's always like a later minus the earlier, or the final minus initial. So you can write kinetic energy of the final minus kinetic energy of the initial. Then what is work? Again, work is the force times the distance that is parallel to the direction of the force. And kinetic energy is 1/2 mv squared. They all have the 1/2 m, so you can factor out the 1/2 m. This will be the final speed square minus initial speed square. So these has to be equal. If you have work, then you can change the kinetic energy, and this is the way that you can find out how much of the force that can actually make this change. So go back to the problem that I just said. Can we just apply this equation to find the solution? So the force to make it to a slowdown is this F. And what is the distance along the direction of the force? Is 1 meter. And that will be equal to the change of kinetic energy. We already calculated the kinetic energy. So which one is the final? Is it 50 or 12.5? This one is the final one. So it's going to be 12.5 joule minus the initial is 50 joule. And you will find out the force is going to be negative because this is a friction force. It will go to the opposite direction. It also tells you the work is going to be negative work because the change of the energy is 37.5 joule, and that's negative. So you have to give the negative work in order to create a slow down motion like this. And that simply tells you this friction, the friction force, this one is the Newton times meter, right? So you can cancel all the meter, you will find out, well, the friction is actually the force, which is negative 37.5 Newton. That is your friction force. Okay, any question about this part here? Okay, this equation is the equation that's important at this point. Later on, once we go to the second part of this chapter, we're going to add some other things into this equation. Besides that, we not only have the kinetic energy, we also have a potential energy. So we can add potential energy into this equation because potential energy is just another kind of energy. And energy can be transformed into different format. Okay, we're not going to cover all kind of a format of the energy. The form of the energy could be chemical energy. It could be like heat. It could be the sound energy, like acoustic energy. It could be a solar energy. There's so many different kinds of energy, but we only focus on the mechanical energy, which include the kinetic and potential. So next one, we're going to cover the potential energy, and we're going to add this one on top of this equation over here. So these are the main topics for this part. Let me just quickly spend like 3 minutes to walk through those example, and then you can watch the video on yourself. So over here, I use several examples to show you how we apply this idea. The first example is that you have 3 balls. They all have the same mass. So 1, 2, 3, you can see on top of the screen. And each one will fall down to the same position, but with a different way. One just goes straight down, which is a free fall. The other one go along a slope. And the other one, the third one, is tied with a string, and that it fall along the string, like doing a circular motion kind of things. And if you want to compare the work, we want you to identify what are the forces acting on the object, and notice that some of the force is not going to do work. And what is the force that will not do work? If the force perpendicular to how it moves, it will never do work. Okay. So that's the thing that you can see from that example. The second thing here is that similar idea that we give different force. The force has a different direction. Then you identify how much work by each one of the force. If the force amount is the same, which one give you the largest work? And you look at how the direction, the force, and the direction of the motion are parallel. As long as they are parallel, and that is the amount of the work that you can calculate it. This one is not going to give you any of the work. As I said, if the force and the motion, which is from the left to the right, they are perpendicular, it's not going to give you any of the work. So case B is not going to give you work. Number 3 is a good way to test your concept about the work again. The scenario is they separate into 4 intervals. And the first interval is you put this like a figure on top of a small car, and you let the car move along the track to the right. When it hits to the barrier, this figure will jump out from the car and it will slide down from the track. And once you leave to the track, at the interval 3, it's going to do like a projectile motion until it hit to the wall. When you hit to the wall, it will be the last interval, it will start to do a free fall. And over here, each one of the box, just want you to write down whether they are greater than 0, equal to 0, or less than 0. Okay, if you can work on this one here, then you have a very good idea about how you can identify the work and how do you know which one is positive, which one is negative. So this is a good example, and I encourage you to follow through this one carefully and think about this by yourself. This requires you to do a free body diagram for all the questions that you see, and I couldn't emphasize more. A free body diagram is so important in this part of the physics. If you are good at the free body diagram, then you will find this is much, much easier to solve a problem if you have a clear picture of the free body diagram. The last one is this one here. This one we will do some calculation. Very similar to the circular motion. You type a light bulb at the end with a string. This also has to use some trigonometry. So the length of the rope is the capital L, 1.1 meter. They give you the angle, and they want you to find out what is the velocity if you start by holding the ball at certain height and you let it go. How do you know how fast it is moving at the bottom of this rope? To solve this problem, you have to use the kinetic energy and work theory, and you're going to have the change of the kinetic energy. Why do you have a change kinetic energy? If you make this one to be the initial, this will be your final state. Do you have the change of kinetic energy? You certainly have, because initially you're holding the bow doesn't have a velocity, so the kinetic energy is equal to 0. When you go down to the bottom, the very bottom, you're going to have a velocity. That means you're going to have a kinetic energy. So you have a change of kinetic energy. What is the reason give you kinetic energy change? The reason is the gravity. Because the gravity is the force try to attract you downwards, and because you actually fall with certain height, and that height is the small d over here. The small d is not easy to find. You have to look at some geometry to find the d, and I explain that in the video, so you can watch the video to find out that. Okay, any question about this? The last thing I want to emphasize is the kinetic energy. The equation for kinetic energy is 1/2 mv squared. Can we have a negative velocity? Well, if you define go to the right to be positive, then you can have a negative, right? Go to the left to be negative. But if you put a positive or negative value into this equation, do you have a possibility to get a negative kinetic energy? No, this kinetic energy is always positive because of the square. When you put a square, it doesn't matter, the v is positive or negative. As long as the object is moving, the kinetic energy is always going to be positive. Okay, remember that kinetic energy will never ever go to negative. It's going to be positive because of the square. So it doesn't matter whether you're moving to the right, move outwards, move downwards. We only care about the value. We don't care about the direction. Okay. Any question about today's lecture? If not, then I will post the example for this chapter, and please watch those examples. And we don't have class on Friday, so the next time we meet is going to be on campus. We're going to do the lab 4. So remember, come to this lab by whatever the group that you are. If you can make change to the second group, please let me know. We do hope that we can have like 2 people move to the afternoon, the second group. All right. If you don't have a question, then I will see you next time.
Thanks.
Thank you very much for coming.